Hi there, so this video is on section 3.4 where we will look at solving exponential and logarithmic equations. So equations where the variable is in the exponent position or equations that have logarithms in them. And we're going to be using what we've talked about in the previous sections, like the different properties of logarithms, the definition of a logarithm, like the two different forms of the log statement in log form as well as in exponential form. And we're doing that in order to solve these equations analytically. Now, we in section 3.1 solved exponential equations graphically, so using our graphing calculator, and that just had limitations. Like, that's a valid skill and it's an important skill to have to be able to solve an equation graphically and using technology. But it does have limitations because oftentimes you end up solving for just an approximation. But now, as we look at these more analytical approaches to solving these equations, we will be able to come up with the exact value or values of solutions. So we're going to start with pretty simple exponential and log equations where we can think about rewriting the equation using something called the one-to-one property, which is pretty straightforward. So one-to-one property says if you have an exponential equation that's in the form of b to the x power equals b to the y power, well, those exponents have to be equal to each other. Like x has to be equal to y. And then the same idea where if we have a log equation where we have log base b of x equals to log base b of y. Now notice that both of those logarithms on the left and the right hand side have the same base. Then the arguments of the logs have to be equal to each other. So by the one-to-one property, this allows us to rewrite the equation with the variables not in the exponent position anymore, or for a log equation, not in the argument of the log anymore. So looking at this first example, pretty straightforward. We have e to the x plus 7 power equals e to the 5th power. So by the one-to-one property, since left-hand side and right-hand side both have a base of e, we can conclude that x plus 7 is equal to 5. And then if we finish solving, so using properties of equality and subtract 7 from each side of the equation, we would get x is equal to -2. And that is our solution. Next equation is a little step up in difficulty because it's not obvious at first glance that one-to-one property could be applied. But looking at the equation closer, we can see that, well, the right-hand side of 4 could actually be written as 2 squared. Now, there are other ways that you could approach solving this equation that we'll talk about in a couple minutes, but it's oftentimes the most efficient to look and be like, can I rewrite this really quickly in order to use one-to-one property or apply one-to-one property? And this equation in particular, yes, we can. So we can rewrite this as 2x squared minus x equals to 2 squared, where then we can say, okay, well, x squared minus x is equal to 2. And now notice that this has become a quadratic equation. The example above in A, we were able to apply one-to-one property and we ended up with a linear equation. Now we have a quadratic equation, so you can use all those different or any of those different methods that are in your toolbox to solve a quadratic equation. I'm going to think about factoring this because factoring by guess and check usually is the fastest approach. But you could technically use quadratic formula if you weren't sure how to factor. So think about what this factors to. That would be -2 plus 1. So we would get x equals to 2 or x equals to -1 as our solutions to this equation. The next equation, so both of those were exponential equations where we could use one-to-one property in order to rewrite the equation into a form that we know how to solve. This next equation is a log equation. And we look in the left-hand side is log. There's no base written, so we know that's log base 10 of x plus 6. equals to the log, again, base 10 of 10x minus 3. So by the one-to-one property, we can rewrite this, let me switch colors here, as x plus 6 equals 10x minus 3. So we've rewritten this equation to be now it looks like a linear equation. The one thing that we need to be aware of is when we are looking at solving the exponential equations, when we think back to exponential functions, like exponential functions have domains of all real numbers. So like the left-hand side or whatever side like has the variable on it, like we know that we could plug any real number in and we would have a real output. Like there's not a domain restriction. So then whenever we end up rewriting as a linear equation, we don't have any sort of domain restrictions to look out for. Like in rewriting in the linear form or the quadratic form, we didn't potentially lose any part of the equation that was causing a domain restriction. However, with log equations, we know we can't take the log of 0 or negative values. Like logs do not have domains of all real numbers. We have to think about like the argument of a logarithm has to be greater than 0. So I compare this to whenever we were solving radical equations and we had to use the strategy of like squaring both sides of the equations. And then whenever we rewrote the equation from there, we lost what was causing a domain restriction. And if we just came into this equation at this step, you'd look there and you'd be like, okay, let's just solve for x. But we wouldn't be thinking about the initial part, like the original equation and the part of that equation that was causing any sort of domain restrictions. So similar to radical equations, and when we had to think about squaring each side of the equation in order to solve for a variable that was underneath the radical, and then we had to think about checking for solutions that didn't make sense. Like solutions that were not actually in the domain, and do a mental check for extraneous solutions. Remember, we called those solutions that don't make sense extraneous solutions. So for log equations, because we will end up rewriting the logarithm without log, like that equation, that statement without a log in it, we do have to think about doing a mental check to make sure that a possible solution is not actually an extraneous solution. So continuing to solve here, like this would be 9x equals to 9. So we get x equals to 1. I'll switch that around. And then we just need to make sure we do a mental. Now you could technically think about what the domain of each side of the equation is here and think about the intersection. So, and check for extraneous solutions in that way. I think it's probably easier when your goal is just to solve an equation and whatever problem it is you're just having to solve. I think it's probably easiest to just do a mental check for extraneous solutions. So think about plugging the 1 back in. Like if we plug the 1 into the log on the left-hand side there, that's log of 7. And then same thing when we plug the 1 in, so log of 10 times 1 minus 3 would also be log of 7. So that works. So the solution to this equation would be x equals to 1. And we were able to get there by applying, thinking about applying the one-to-one property. Okay, so now we are going to look at some more, I guess, complicated exponential and log equations, like log and exponential equations where we cannot apply the one-to-one property. There are different perspectives that we can use. I'm going to show you with the first example here, those 3 different perspectives that you can use in order to solve for a variable that's in the exponent position. And it's really up to you what you see and what you're the most comfortable with. But we might be thinking about applying these inverse properties of logarithms that we talked about in the previous section, or we might be thinking about the definition of a logarithm, right? That log base b of x is equal to y. That would be thinking about this statement in log form, and b to the y power is equal to x. Okay, so going from one form to the other for these different equations. So that's the approach that I typically use. Like looking at this equation, I would first go, can I rewrite the right-hand side here? Can I rewrite 27 as 5 to a power easily? No. So I can't use the one-to-one property, which means I have to pick one of the other approaches, like one of the other perspectives in order to get that variable that's in the exponent position out of the exponent position. And the approach that I'm going to use first here is rewriting this statement, this equation, which is in exponential form, in its equivalent log form. Okay, referencing that definition of a logarithm. So that would be y squared equals to the log base 5 of 27. And you could always double check that. Draw your little arrows. 5 to the y squared is equal to 27, right? This is the same statement. And then we would have y equals to plus or minus the square root of log base 5 of 27. So 2 different solutions. I'm okay with you leaving like so, but technically that is 2 different solutions that could be separated. Or y equals to the negative square root of log base 5 of 27. Now, the approach that I think your textbook uses, many textbooks show, is using those inverse properties. Okay, so looking at this and being like, okay, well, that's 5 to the y squared power equals to 27. That means I'm going to think about taking the log base 5 of each side of the equation. Okay, and then hopefully you see now we have, this is that inverse property. These are the same base. So that would simplify to be y squared. You could also think about plugging the left-hand side there to rewrite that as y squared times log base 5 of 5. And you know log base 5 of 5 is 1. But either way, this turns into y squared equals to the log base 5 of 27, which is what we pass through using the other perspective. And you can see that we get the same 2 solutions. The last approach that you could use, and to me this is a little bit more, kind of more old school, but like it's fine. And part of the reason for this would maybe be because this approach would be because like your calculator has that log base 10 button and that natural log, so the log base e button on it. So if you're wanting to just use either of those, like think about taking the log base 10 of each side of the equation or the natural log of each side of the equation, that is also an option. You could technically take the log base 100 of each side of the equation or the log base pi of each side of the equation, and it would work. But if we took, so I'm just going to show this taking the log of each side of the equation here. And I compare this to like squaring both sides of the equation, like that sort of approach to allow us to rewrite the equation in a different form that is in a form that then we know how to use properties of equality to solve. So from here, the left-hand side, we can think about using that power rule for logarithms. We can plug the left-hand side. So we would have y squared times log of 5 equals to log of 27. And then when we divide by log of 5, we're going to pause here for a second. Notice that we're at the point where we have y squared on the left-hand side. Log of 27 over log of 5 is the same as the log base 5 of 27 by the change of base formula. So this actually is, those are the same two values. You type them into your calculator, you would get the same values. So we can just say this is y equals to plus or minus the square root of log of 27 over log of 5, which if you wanted to, you could rewrite that as the square root of log base 5 of 27. There's not really a good reason to. So those are the different approaches you can use. If you would like to pause the video and try some of these next ones, using the approach that you feel the most comfortable with, and then you can play and check your answers. You can try that. So next equation, 4 to the 3x plus 2 power equals to 7. I think, well, I cannot write 7 as 4 to a power easily. So what I'm going to do is I'm going to think about rewriting this in log form. So 3x plus 2 would be equal to the log base 4 of 7. And again, you are always welcome to do the little check, like, yep, I rewrote that the correct way. And now we have the x out of the exponent position, so we can just use properties of equality. So we could subtract by 2 on each side of the equation. And then we could think about dividing by 3. Here, I'm just going to give myself more space here. We could divide by 3. So log base 4 of 7 minus 2 all over 3. And you could type that into your calculator, get the approximation, but this would be the exact value to that solution. Okay, now this is a little bit different. Notice we have a 4 times e to the x squared power equals to 64. We cannot rewrite this equation quite yet in its equivalent log form. We would have to think about dividing by 4. We need to get that base raised to a power by itself on one side of the equation before we can use that definition. So then we have e to the x squared equals to 16. Now thinking about rewriting in log form, so we'd have x squared equals to the natural log of 16. You could also think about taking the natural log of each side of this equation from that perspective. That's fine. And we would have x equals to plus or minus the square root of ln of 16. Again, if you would like to pause and try this one on your own before you check your answer. So you can either think about taking the log base 10 of each side of the equation, or I'm going to just rewrite this as 2x minus 3 equals to the log of 12. Right, 10 to the 2x minus 3 power is equal to 12. Okay, so adding 3 to each side of the equation, and you are welcome to go directly to also dividing by 2. Like if you want to do the algebra in one step, that's totally fine. So log of 12, I keep leaving that one off, plus 3 divided by 2. This is what I call a quadratic-like exponential equation. And you'll see that we'll run into different types, like we'll run into trig equations that I think of as being quadratic-like as well. Meaning you can kind of approach them, like rewriting them the same way that you would a quadratic. So like you could think about factoring, you could think about using quadratic formula. Oftentimes students like to use a strategy that will come up again as a method in calculus for integration called U substitution. And when I hear the word U substitution, or the words U substitution, I usually think about that method for integration in calculus. But it's the same idea behind it, where you're thinking about letting part of the equation equal to U so that you can rewrite the equation in a more familiar form, like a visually more familiar form that makes it easier to kind of wrap your brain around the process that you're doing and is just more familiar to you. So for example, if we did a U substitution here, we would think about letting U equal to e to the x so that we can rewrite the left-hand side of the equation here as U squared minus 4U plus 3 equals to 0. And you could do a little mental check, like if you were to substitute the e to the x back in, that would end up being our original equation. So from here, we're like, oh, well, I know how to factor this, right? That would be U minus 3U minus 1. And then by the zero product property, that would be U equals to 3 or U equals to 1. We're not done though. So now we're at the point where we're like, okay, well, we can substitute e to the x back in. So we'd have e to the x equals to 3 or e to the x equals to 1. The left equation here, e to the x equals to 3, rewriting that as x equals to natural log of 3, either taking natural log of each side of the equation or rewriting in log form. And this equation over here, you can either think about taking the natural log of each side of the equation or rewriting as x equals to ln of 1, but you need to remember log base anything of 1 is 0. This can also be solved by inspection. Just looking and going, hey, x would have to be equal to 0. Now, you do not have to do the U substitution. If you had seen this, and I think some people get to the point where they are more comfortable just being like, oh, well, that's quadratic. Like I can think about factoring that, saving like one step, but thinking, okay, well, to get that e to the 2x, I would have to have e to the x and e to the x. Okay, and then that would have to be minus 3 minus 1. So you get e to the x equals to 3 or e to the x equals to 1 by the zero product property. And then the same thing. We end up with the same solutions. So U substitution is not required here, but it is, anytime you're hearing U sub, the idea is rewriting the equation in a form that is more familiar, like that's simpler and more familiar to you, so then you can solve from there or use like what you already know in order to solve from there. This next equation, notice that the variable x is in the exponent position, but it's also in the denominator. So we need to first think about getting 3 minus e to the 3x out of the denominator. We can do that by multiplying by 3 minus e to the 3x power on each side of the equation. And if you are writing down this step, please put grouping symbols around the 3 minus e to the 3x on both sides of the equation when you multiply. And you also must show that you are applying the multiplication property of equality by multiplying by the same thing on each side of the equation. If you are showing this step, you need to show it in this way. If you are just mentally doing this step, that's fine. But if you are going to show this step, you must do that. If you go directly to here, oops, what am I doing? That's fine. But just please don't just only show like multiplying by one side or not having the grouping symbols. I will dock for notation on that. From here, you also have options. You could technically distribute the 8 and then use the properties of equality to try and isolate the e to the 3x. I'm going to think about dividing by 8 so that this turns into 1/2 equals 3 minus e to the 3x. And then if I'm subtracting by 3 on each side of the equation, that would be subtracting by 6/2. So that would be minus 5/2 on the left-hand side equals to negative e to the 3x. If we think about dividing by -1, that turns into 5/2 equals e to the 3x. And then rewriting in log form, that's 3x equals to natural log of 5/2. And dividing by 3. So x equals to the natural log of 5/2 divided by 3, which if you wanted, so we're done. If you wanted to unplug that and rewrite as like ln of the cube root of 5/2, or like let's say that this is a multiple choice question, then you could see it in that form. You have like the different properties of logarithms to rewrite this in different forms. So those were some different exponential equations to practice solving. Let's look at this more complicated logarithmic equation. Looking at the equation at first glance, we're like, well, we can't use one-to-one property, because my go-to is to think, can I use one-to-one property? The reason I cannot use one-to-one property the way that this is written is the right-hand side is a sum of logarithms. So we do have a way to rewrite the right-hand side as ln of a single argument. We can use that product rule for logarithms. So we would have ln of x plus 8 equals to ln of x times x plus 3. From here, we can apply the one-to-one property for logarithms and rewrite this as x plus 8. So without the natural log, I'm going to think about distributing that x in, so x squared plus 3x. Remember though, because we are dropping the log, which has a domain restriction, we do need to think about checking for extraneous solutions at the end. But right now, this is a quadratic equation, which you should be very comfortable with solving. Okay, thinking, does this factor? I believe it does. What would that be? Plus 4 minus 2. So we would get x equals to -4 or x equals to +2. And then just doing a mental check in the original equation. So I see right away, -4 is not going to work, because if we plug in -4 into ln of x, or here, right, that ends up being natural log of a negative value. That doesn't work. This is extraneous. And then thinking about plugging in 2. 2 should work. 2 is okay. So 2 is the only solution to that equation. But we had to think about checking for the extraneous solutions. If you would like, you could try this one on your own, like pause and try it on your own. It is a little bit different because, from the last example, because of this constant that's in here. Like we didn't have a constant in the other one. Color should we use here? We'll use blue. Before we could think about applying any properties, and there are some different perspectives we could use. I like to go back to the definition, and I would be thinking, okay, this is an equation in log form, and then to get the variable out of the argument position, I would rewrite in exponential form. But before we can do that, we need to combine the logarithms on the left-hand side. To do that, because that's subtraction happening between those two logarithms on the left, we can use the quotient. I don't know what I'm writing. We can use that quotient property for logarithms and rewrite the left-hand side as log base 2 of 4x, so the over x minus 1. So the argument becomes the quotient. A common mistake I see is for people to rewrite that as log base 2 of 4x over log base 2 of x minus 1. That doesn't so much help. So using that quotient property for logarithms. And then now we can think, okay, 2 cubed would be equal to 4x over x minus 1. So 2 cubed would be equal to 4x over x minus 1. And then solving from there, I can think about multiplying by x minus 1 on each side of the equation. 2 cubed is 8. And distributing the 8. Okay, so that would be 4x equals to 8. And I end up with x is equal to positive 2. This is a log equation, so I have to think about checking. Plugging 2 in, that looks okay. That'll work. Log base 2 of 8 minus log base 2 of 1, which would be 0. And then log base 2 of 8 would be 3. So that works. Okay, similar strategy of rewriting in the exponential form. Nothing else to combine. We have, remember, ln is log base e. So e to the 7th equals to 3 minus x squared. Remember, e is just a constant. It's Euler's number. So e to the 7th power, that's just a constant as well. So we can actually use a square root property here in order to solve for x. So I think I might actually add x squared on each side of the equation. And then also think about subtracting e to the 7th on each side. And then from here, I can say x is equal to plus or minus the square root of 3 minus e to the 7th power. Here's the thing. When we go to check, we might want to check and think about, it might even be helpful to come up with what the decimal approximation of this is. Now, e to the 7th power is a large number. 3 minus that number is going to be less than 0. So the square root of that negative number is actually not a real number. So actually neither of these values are solutions here. Okay, there's no real solutions. To that equation. Okay, log base, multiple terms with log base 5. Can't use one-to-one property until we have a single logarithm on one side. Now, we could just leave this equation written as is and use the quotient property for logarithms on the left-hand side. We could also think about adding log base 5 of x minus 1 to each side of the equation, and then you could use the product property for logarithms. I'm going to leave as is, but you can, either method would work. So the left-hand side here would be written as log base 5 of x plus 1 over x minus 1 equals to the log base 5 of x. And now we're at the point. So when we have the log statement on both sides of the equation, that's when you're trying to use one-to-one property. If we have a constant on one side of the equation and a log on the other, that's when we're wanting to think about rewriting in exponential form. So this can be rewritten without the log base 5 by the one-to-one property as x plus 1 over x minus 1 equals to x. Now this is a rational equation. So we can multiply by x minus 1 on each side. So x squared minus x when we do that on the right-hand side of the equation. We have a quadratic equation now. So using what we know to solve a quadratic equation, I apologize, my husband's computer keeps making sounds. So we have x squared, does that factor? No, it does not. Okay, so that means we're going to use our handy-dandy quadratic formula. So we would have x equals negative b, so that'll be 2 plus or minus the square root of b squared minus 4ac all over 2a. Okay, I'm going to split that. So we would have x equals to 2 plus the square root of 8 over 2, or x equals to 2 minus the square root of 8 over 2. And we know the square root of 8 can be rewritten as 2 root 2. So this could actually be written as x equals to 1 plus root 2. And this would be x equals to 1 minus root 2. So thinking about checking for extraneous solutions, so 1 plus root 2 will be fine, but 1 minus root 2 would cause us to have to take the log of a negative value. So 1 minus root 2 is extraneous. 1 plus root 2 is the actual solution. So again, this is extraneous. It does not make sense as a solution. And again, the reason we pass through that is because our strategies for solving these equations have us rewriting the equations in these forms that don't have the same domain restrictions as the original equation. Okay, so that looks like that's all of our examples. Just to review again, we were able to use the one-to-one property when we thought about having a log with the same base on each side of the equation versus this example or the previous one where we had a constant there, and that's whenever you're trying to rewrite the equation so that you have a log on one side, the constant on the other, and then you can rewrite in the exponential form and solve from there.